Every 44 minutes, something in our galaxy switches on. For about 2 minutes, it flashes in radio waves and X-rays at the same time. It rotates too slowly for an ordinary pulsar, does not fit comfortably as a magnetar, and has not behaved like a normal white dwarf system either. Astronomers know where it is and exactly when it will return. They still do not know what it is. Reaching that object requires passing 7 earlier signals, including 2 that never came from space at all. Number 8. Perytons. In the late 1990s and 2000s, the Parkes Radio Telescope in Australia detected brief signals that resembled fast radio bursts. Their frequencies swept downward in a way normally produced when a pulse travels through ionized material in space. The name peryton came from a mythical winged creature because radio astronomers remain dangerous when allowed near folklore. The signals had suspicious habits. They appeared during daytime and seemed to arrive from many directions at once. That pointed to something near the telescope, not a distant object in one fixed part of the sky. A new interference monitor finally detected activity around 2.5 gigahertz. Researchers tested equipment around the observatory and reproduced the signal by opening a microwave oven before its cycle finished. During shutdown, escaping radio energy created the same sweeping pattern. The discovery mattered because genuine fast radio bursts show a similar downward sweep in frequency after traveling through material in space. Once the microwave imitation was identified, astronomers could build better filters for the real events. Lunch had not discovered a new branch of astrophysics, but it had successfully impersonated one. Number 7. BLC-1. In 2019, the Breakthrough Listen project observed Proxima Centauri, the nearest star beyond the Sun. In the data was a narrow signal near 982 MHz. It appeared during pointings toward the star, drifted in frequency, and lasted for hours. Those are exactly the properties that force a SETI team to become extremely suspicious of its own equipment. The candidate was named Breakthrough Listen Candidate 1, or BLC-1. Detailed analysis found dozens of similar signals at related frequencies. They formed a pattern produced when human transmitters or electronic oscillators mix and create additional frequencies, the radio equivalent of 2 sounds combining to produce an unwanted third tone. BLC-1 was local interference, not a transmitter at Proxima Centauri, but it passed enough early tests to become a valuable rehearsal. A convincing extraterrestrial candidate must return, remain tied to one place in the sky, appear at other telescopes, and survive every explanation involving electronics, satellites, aircraft, and somebody reheating food. Number 6. The WOW signal. On August 15, 1977, Ohio State University's Big Ear telescope recorded a strong, narrow-band signal near the frequency of neutral hydrogen. As Earth rotated, the signal rose and fell in a pattern matching a fixed point passing through the telescope beam. Volunteer astronomer Jerry Eman found the sequence 6EQUJ5 on a printout, circled it, and wrote "WOW" beside it. The event lasted 72 seconds, the full observation window for that position. It was not detected in the telescope's second beam and never returned despite repeated searches. Proposed explanations include human interference, an unusual natural radio source, reflections from debris, and emission connected with hydrogen clouds or comets. None reproduces every important detail well enough to close the case. The SETI Institute still classifies it as unsolved, which is not the same thing as alien. One unrepeatable signal cannot support an extraordinary conclusion, the WOW signal is famous precisely because the evidence is both intriguing and permanently incomplete. Number 5. The magnetar burst. Fast radio bursts, or FRBs, release intense radio energy for milliseconds. Most come from distant galaxies. For years, their sources were unknown because the events ended before telescopes could coordinate. Then, in April 2020, a magnetar inside the Milky Way called SGR 1935+2154 emitted a powerful radio burst. Space telescopes detected a related X-ray event. It was weaker than many bursts arriving from distant galaxies, but powerful enough to show that magnetars can produce the same basic kind of event. A magnetar is the collapsed core of a star wrapped in an extreme magnetic field. Movement in its crust or field can release enormous energy and disturb the charged particles around it. This solved one major question without solving the entire class. Fast radio bursts occur in different environments. Some repeat, others have not, and the exact process that turns magnetic energy into such an organized radio flash remains debated. Astronomy found one working engine, not one answer for every burst. Number 4. GLEAM-X J1839. While examining archival data from the Murchison Wide Field Array, astronomers found a source that turned on every 18.18 minutes. Each appearance lasted roughly 30 to 60 seconds and was strongly polarized. During some pulses, rapid subbursts appeared inside the larger signal. Ordinary radio pulsars are rotating neutron stars whose beams sweep across Earth every fraction of a second or every few seconds. As they slow down, standard models predict that the electrical conditions needed to make a bright radio beam should eventually fail. An 18-minute period is far beyond that comfortable range. An extremely slow magnetar was proposed, but models struggle to produce such bright, orderly radio pulses from something rotating so slowly. The source remained active for only a few months in 2018, then disappeared from later observations. It behaved like a lighthouse that rotates too slowly to keep its lamp powered, ran for one season, and left before maintenance arrived. Number 3. GPM J1839 -10. Another object flashes every 21 minutes. Its pulses last between 30 seconds and 5 minutes, vary enormously in brightness, and contain smaller repeating structures. This time, the source did not vanish. After its discovery, astronomers searched old observations and found pulses extending back to at least 1988. It had been operating for more than 3 decades, while remaining unnoticed inside archived data. The long period suggests either a slowly rotating neutron star or a magnetic white dwarf. The neutron star problem is power. At this speed, standard theory says it should be too weak to maintain the particle activity behind a radio beam. A white dwarf can rotate slowly, more comfortably, but then the brightness and other details become harder to explain. The signal is not evidence of engineering. It is evidence that the current menu of stellar engines is missing a page, and the next 2 objects make the missing section larger. Number 2. ASKAP J1935+2148 repeats every 53.8 minutes and changes personality while doing it. In one state, it emits bright pulses lasting 10 to 50 seconds. In another, it produces much weaker flashes, only a fraction of a second long, with a different polarization pattern. At other times, it becomes radio silent. The object changed between these states over months. Mode switching resembles behavior seen in neutron stars, but the rotation period is uncomfortably long for standard pulsar emission. An isolated magnetic white dwarf was considered, yet constraints from the period and source size create problems for that explanation as well. In 2026, astronomers confirmed that a different slow radio transient is an accreting white dwarf pulling material from a companion. That proved these signals do not all share one origin. Similar rhythms can come from entirely different stellar machines. The category was supposed to classify the mystery. It has started collecting mysteries instead. Number 1. ASKAP J18320911 lies inside our galaxy and repeats every 44.2 minutes. During an active phase, it produces bright radio emission for about 2 minutes. The Chandra telescope found X-ray pulses on the same schedule, and both kinds of emission brightened and faded together. Whatever the engine is, one object is producing both signals. An old magnetar could provide violent magnetic activity, but the slow rotation and required energy strain ordinary models. A highly magnetic white dwarf can rotate slowly, but producing both the X-rays and the organized radio pulses is difficult. A binary system became more plausible after the 2026 white dwarf discovery, yet no ordinary companion has completed the explanation for this object. The object also changed dramatically. Archival X-ray observations before the outburst showed no comparable source, and later observations placed strong limits on its quiet emission. Whatever the engine is, it can enter an unusually energetic state and then fade. This is not a message. The pulses contain no decoded language, mathematical sequence, or evidence of technological modulation. Signal in astronomy means measurable radiation, not an intentional greeting. The real mystery is better than a hidden message. Telescopes are finding objects that rotate too slowly, switch between different states, and combine radio waves with X-rays in ways that cross the boundaries between pulsars, magnetars, and white dwarf binaries. The sky is not sending us a sentence. It is showing us that our filing system was built before we had seen everything that needed filing.